Okay, so welcome to everybody. So our fourth talk of the day is by Yihui Quek from Stanford. He's going to talk, this is a merged talk on two papers she submitted. So we've got quantum algorithm for Petz recovery channels and pretty good measurements, and faster quantum polar decomposition, Procrustes and pretty good measurements. Yihui has informed me that the talks have kind of been genuinely merged, so it won't be a case of doing one talk, stopping and having some questions doing the other. We'll go all the way through, and if you can post any questions in the Slack channel, then I'll put them to Yihui at the end. So welcome again to Yihui, and please start your talk when you're ready.
Oh, okay. So actually, I'll be talking about two separate algorithms, so I can actually stop after the first one, even though that won't really be the end of it. So I can stop after the first one and you can ask me questions if that's convenient. Well, okay. Hi, everyone. My name is Yihui. I'm from Stanford. Thank you to the organizers for having me here. As Stephen mentioned, my talk today is a merge talk. And in this talk, I will present two quantum algorithms, one quantum algorithm for Petz recovery channels, and another quantum algorithm for the polar decomposition. And the reason these two talks, or the reason it made sense to merge these two talks, is because both of these quantum algorithms have at their core the quantum singular value transformation. So we'll be seeing that this recently discovered toolbox of the quantum singular value transformation actually is very useful in the sense that it provides a rigorous and systematic way in which we can bring some theoretical tools to life in the sense that we can now implement them on a fault-tolerant quantum computer. So without further ado, so I'll start off with a summary of both results. For the first result, we use the quantum singular value transformation, we use the quantum singular value transformation to provide quantum algorithms for the following two tools. The first is polar decomposition, which comes from classical linear algebra. And you can actually think of that as a decomposition of a matrix, which is the analog of how you would decompose a complex number, Z, as R e to the I theta. And I'm going to make this more precise later, of course. Now, the second quantum algorithm we'll talk about is one that implements a tool from quantum information, namely the Petz recovery map. And this map is one that approximately reverses a quantum noise channel. As an application, it turns out that both of these algorithms I'll talk about today lead to the implementation of a third tool, which is called the pretty good measurement. And this pretty good measurement is a tool that you see a lot in proofs of sample complexity of quantum algorithms. And what our contribution is to show how to implement this tool. So first, we'll introduce the commonality between these two algorithms, which is the quantum singular value transform. Now, the quantum singular value transform is an algorithm that manipulates block encodings. Now, what is a block encoding? Well, given a complex matrix A, note that A does not have to be Hermitian. You can embed A in the top left-hand corner of a unitary. And you call such a unitary a block encoding of A. So you can rewrite this embedded A in the form shown on the right-hand side of that equation. And the significance of this in terms of quantum algorithms is that if you are able to encode A as the top left-hand corner of such a unitary, well, then let's say that A is an operator that acts on A qubits, then you can actually use this unitary U to realize a probabilistic implementation of A. And here I've also made it as general as possible by including this constant alpha. Alpha is called the subnormalization factor, but for the purposes of this slide, you can just set alpha to 1. Okay, so the way this works is that on an A qubit input psi, you would apply the block encoded A, which is the unitary U, to an A qubit input tensored with S ancillas, all in the 0 state. And then just by matrix multiplication, you can work it out. It's clear that what this results in is a new state such that if you measure the ancilla after you apply U, then if the outcome was the all zero state, then what you're left with in your system of A qubits is a state that is proportional to A psi. In this way, the block-encoded unitary is actually a way of applying A to the state psi, or transforming A to the state psi. And the really cool thing is that A itself does not have to be unitary. So you can actually transform quantum states by things that are not unitary. Of course, in that case, then you may get a state that is not exactly A psi, but a state, because A psi itself may not be normalized, but what you would get is a state proportional to A psi. And then you would just have to do some amplitude amplification to get that state. So what exactly is quantum singular value transformation? So now I've introduced the concept of block encodings. The singular value transformation is a way to transform the singular values of block encodings. And what I mean by that is really the singular values of the A that we had just now. So you can think of this method as kind of like a black box in which you choose a polynomial, f tilde, by which you want to transform the singular values of A by. In this case, with some loss of generality, I've assumed that A is a density operator. So I want to transform the singular values of the density operator by some polynomial, f tilde. So the quantum singular value transform says that once I've managed to block encode this density operator, then I can transform its singular values by this polynomial. And that results in a new block encoded unitary, which is f tilde rho. And the circuit I've shown above is just like the circuit that implements this. Of course, phi is a function of, like, you see that this circuit consists of alternating the original U, which is the original block encoded rho, with e to the I phi n, e to the I phi I, 2 pi tilde minus I, and the entire vector of phases phi is a function of the polynomial that you would like to transform the singular values of rho by. And just one point, in terms of practical implementation, usually what we want to transform, usually the function that we want to apply to the singular values may not necessarily be a polynomial. In that case, it suffices to use a polynomial approximation of the ideal function f. So just to repeat, the quantum singular value transformation is a technique that compiles applications of U rho into an application of essentially U f tilde rho. And the gate complexity of this technique is measured in the number of uses of the original block encoded density matrix U rho. And it also depends on, so like I said just now, because often we'll be using an f tilde that is actually an approximation of a polynomial approximation of an ideal f. So the accuracy of this transform depends on the approximation domain and the error of the approximation. So just as an example, let's say that I want to approximate the polynomial x to the half with some error. And the error is, well, okay, so the error is delta in this case, and I guess the norm there refers to the maximum value of the difference between f tilde x and x to the half on this interval lambda min to 1, where lambda min is the minimum singular value of rho. So we can define, so 1 over lambda min rho, we will call the condition number. And the reason we call it the condition number is that this is kind of, or this parameter kind of limits how difficult or easy it is to do the transformation. And you can see that the overall gate complexity scales linearly in the condition number, kappa, as well as in log 1 over delta. And it turns out that delta will be linearly related to the final error of the quantum singular value transform as well. And the gate complexity is, of course, measured in the number of uses of the original U rho. So the setting is that I'm able to implement U rho, and then by doing this quantum singular value transform, it gives me a way to implement U f tilde rho instead. And okay, so you can check out our paper on the archive. This is a paper with Andras, Seth, Iman, and Mark. So just to give some classical intuition for what the Petz recovery map is. So you can think of a classical channel as applying a conditional probability onto an input, which is a random variable x distributed according to px. And what you get is an output y, which is distributed as py, which is given by that expression I've written down there. So one could ask the question, if I know two things, the input distribution px and the channel py given x, then what is px given y? And the answer to this is something that we've all studied in probability class. It's just use Bayes' theorem to write down p of x given y, right? So p of x given y can be written down as a function of px and py given x, as well as py, but py is just a function of px and py given x. So quantumly, we can also think about quantum states as being the quantum generalizations of probability distributions, and quantum channels as being the quantum generalizations of py given x. Yes, py given x. So the Petz recovery channel is defined as the quantum analog to the above. So it has the expression that I've written down below. It's slightly complicated, but if you squint, you can actually see that it's the same thing. It reduces to the classical expression. So so sigma A, that is the quantum analog of px, and dagger, that is the quantum analog of p of y given x, and n applied to sigma A, that is what happens when I send the input state through the channel, that gives me the output, and that is the quantum analog of py. So here's why you should care about the Petz map. Well, the first is that the Petz map is a universal recovery operation in error correction. The second is that it's actually a really important proof tool in QI. So you can actually use the Petz map in a decoder for a quantum communication channel. And in fact, this use of this Petz map actually gives you some nice theoretical properties, such as it achieves the coherent information rate for this channel. It actually even has implications in quantum gravity. So the specific line of research that uses the Petz map, or at least one of the lines of research that I know, is entanglement wedge reconstruction. And that's a diagram of an entanglement wedge being reconstructed. And also, the form of the Petz map is, like I said just now, the Petz map is kind of like the quantum equivalent of Bayes' theorem. So actually, the operations that you require in the Petz map can also be used to do something called quantum Bayesian inference. And you can look at the paper I've linked. They call this the star product. And it turns out that this kind of operation is found in a whole host of quantum information processing tasks. So there may be a lot of scope to expand what we've done. And also, I guess it also includes the pretty good measurements as a special case, and we'll talk about this later. So I'm just going to give a quick primer on quantum Shannon theory. So a quantum channel is a physically valid map bringing one quantum state to another. And the reason it's important to study quantum channels is because that functions as a model for quantum noise. And for example, we can think of quantum noise acting as an amplitude damping channel. So the Petz map is something that reverses such a quantum channel, which is precisely why it's used in quantum error correction, if you think of quantum channels as being like quantum noise. So there is this theorem which gives you an easier way to represent a quantum channel. It's the Troy-Cross theorem, and it says that any physically valid channel can be decomposed as a sum over terms of the form VL XA VL dagger, where XA is the input state. So the key thing here is that you have these operators VL, and they have to sum to the identity. Or if you take the sum of VL dagger VL, that has to be the identity. And it turns out that this is actually a much more convenient way of writing a quantum channel, and we'll also use it later. So the cross operator representation, like I said, is very useful. And one familiar example is unitary evolution, which has only a single cross operator, u. So you can see that u row acts as u row, u dagger. So that's already in the form that we had just now. And another thing that I wanted to say is there is also this notion of a channel adjoint. And the channel adjoint, which is defined with respect to any channel n, is just a matrix that satisfies y and x is equal to n dagger y x, where the brackets represent the typical inner product between two matrices. So you can actually write down the adjoint of a channel explicitly using the cross operators. So n dagger y. So n dagger y is VL dagger. It's a sum over VL dagger y VL. And what we had just now was ny was the same thing, but with the dagger and the non-dagger switched. So this is another reason why the cross operator representation is very useful. So we're going to implement the Petz map, which I showed a couple of slides ago. And just for completeness sake, I'm going to state the assumptions. So the Petz map is a function of an input state and the channel n. And what we need in order to realize a Petz map is a block encoding of the input state, which we'll call u sigma, and also a block encoding of some state, which is the output of the channel acting on the input state. Another thing we need is a unitary extension of the forward channel n. So I didn't talk about this just now, but a unitary extension is something like a Stein spring dilation. Basically, it just says that you can regard every channel as a unitary acting on a larger space. And then if you take a trace over the environment system, then you get back the action of the original channel. And basically the unitary acting on the larger space is the unitary extension of the channel. So why is this realistic that we would have a unitary extension of the channel? Well, I guess the idea is that if your channel represents noise and you want to kind of reverse the noise, then maybe you've already kind of characterized the noise and you're able to simulate it using quantum gates, but quantum gates are unitaries. So the simulation would be you would have to simulate the unitary extension of the noise channel. Okay, so here's the Petz recovery map again. So given a quantum state sigma A, which is the implicit input to the channel. Okay, so just to clarify, there are two kinds of inputs. The first is the implicit input, which is sigma A. And this input doesn't change. So the Petz map is defined as like a function of this implicit input and the quantum channel. But in general, you want to apply the Petz map to an arbitrary input, and that's the omega here. So the Petz map has this form, and you can understand it as, or you can break this down by decomposing it into three maps. The first map is conjugating an input state omega b by n sigma a to the minus half. The second map, so the second map is, I'm not sure if you can see my cursor, but the second map is applying the n dagger, so that's the adjoint of the channel n, to what we have to the output of the first map. And the last map is conjugating that by sigma a to the half. And each of these maps is not trace preserving, but their composition is trace preserving. So the second step of the map is a little bit tricky because it's not extremely clear how to implement the channel adjoint if all you have is a unitary extension of the channel. But you can actually just rewrite the adjoint in terms of this. And there's a small issue here, which is that if you look at this rewriting, omega b has to be tensored with an identity on the environment. But the identity on the environment is not actually a quantum state. So what do you do? Well, it turns out that you can just act on the maximally entangled state because its density matrix is proportional to the identity. Okay, so now I'm going to kind of quickly go over the algorithm. How much time do I have left?
We've got 15 minutes, but I mean, we can overrun a little bit if certainly feel free to take the 15 minutes for the talk, and then we can do questions after that.
Okay, great. So what we're actually going to do is we're going to implement an isometric extension of the Petz map. And I realized that this horrendous expression here may not be very similar to what I showed you on the previous slide, but you can look at our paper to reassure yourself that it actually is the same thing. So you're supposed to read this from the right to the left. So IB is the place where you put your input state, but we're talking about implementing the map, so that's why we've put a placeholder identity here. Okay, so what you have to do is you have to tensor that with the maximally entangled state. And then we have the three operations, and now I'll go through the three operations. So the first operation, you're supposed to read this as kind of like, so V is kind of like a Krauss operator, okay? So the first operation here is the conjugation with n sigma a to the minus half. The second operation, which I've highlighted in yellow, is the complicated stuff that we have to do in order to implement the adjoint. And like I said just now, what that means is that you have to tensor in this maximally entangled state to your system, B, and then you have to apply this Steinspring dilation of the channel, UN. And then in the end, what you're going to have to do is you're going to have to conclude with a measurement, but I'll talk more about that later. And also, this stuff in green is the equivalent of the third thing that I had just now, which is conjugation with sigma a to the half. So the thing is that you have to conclude by tracing over the environment E tilde, and you can actually just achieve this by ignoring the environment. So I'll go into more detail about how the QSVT is used to accomplish this, but let me just state formally the theorem. So like I said, the Petz map is a function of the forward channel and an implicit input state sigma a. And we can accomplish an approximation P tilde of the Petz map P such that in diamond norm, the difference is less than epsilon. And what we care about is the gate complexity, but the gate complexity is in terms of like the building blocks that we had. And the building blocks are basically this unitary that implements the isometric extension of N, and also these two block encodings of sigma A and N sigma A respectively. So the key thing to note here is this scaling. Well, DE is kind of an environment system, which is at least the Krauss rank of the channel. And so like you can basically focus on equation 5, the number of users of this kind of channel. So UN, I said, was an isometric extension of the channel, but you should think of it as really being the representation of the channel itself. The number of users of that is square root DE times kappa n sigma, which I remind you is 1 over the minimum singular value of n sigma. Oh yeah, and I omitted this part, but actually we proved in our paper that this scaling is quite close to optimal, the one that we have in equation 5. So let's focus now on maps 1 and 3. That's pretty straightforward, right? Because you can easily see that with the singular value transform, all you need, so we assume that we had this U n sigma, which takes the form of this block encoded n sigma. And with quantum singular value transform, you just immediately are able to transform that into n sigma to the minus half by approximating the function x to the minus half. And that requires, well, on the order of kappa n sigma users of this unitary here. And the third map is, again, the same story. You use this quantum singular value transform to transform the singular values from sigma a to sigma a to the half. And this requires kappa sigma users of U sigma. So I'm not sure if you guys remember, but like a long time ago, I said that the complexity of the singular value transform scales basically linearly in the condition number kappa of whatever is block encoded here. And you can see that these gate complexities actually reflect that. So now we're going to focus on how to implement the second map, which I remind you is our way of rewriting the channel adjoint. Oh, I left out the dagger in the title of this slide. So I've broken it down into steps. So the first two steps are to firstly tensor in the maximally entangled state gamma, and next to just perform UN dagger. So we assume that we could implement UN. UN dagger is just like the inverse of that. So all of this is very easy and you don't need to use the QSVT. But the last step is actually slightly more involved in the sense that the last step corresponds to measuring the system E prime and accepting if the all zeros outcome occurs. And in effect, this means that you have to post-select onto the zero state. And you also have to ignore the system E tilde. And the interesting thing is that this last step here, so the first two steps were kind of like these two blobs here, but there's an intervening sigma A to the half, right? You see between this and this. So the sigma A to the half, actually, I already explained just now. That's, you can just implement that by doing so that was what I called map 3. And that's just the quantum singular value transform applied to the block encoding of sigma A. Now, map 2, it turns out, consists of two parts. And the first part has to happen before map 3, and the second part happens after map 3. So this is what I just explained. So you have to do these last two steps after map 3. And I think, so the first two steps were easy, and the last two steps of map 2 require you to post-select. Now, how do we do the post-selection? Well, okay, so it turns out that after implementing map 1, the first two steps of map 2 and map 3, what we create is a gigantic unitary, which has the form given here. So this unitary is a block encoding of something which is an approximation to the ideal Petz map. And there are all these factors in front. These factors in this case are very important. So that's what that alpha was that I had on like multiple slides ago. But what this alpha tells you is that tells you the probability of getting the correct state. So like I said just now, you're going to have to post-select on your ancilla, when your ancillae being in the zero state. And the subnormalization factor here, which is this bunch of constants, that actually tells you the probability of success of getting the correct state. So this is, so if I were to just implement this, this would be probabilistic. I don't always get the correct state, so this is a problem. But luckily, amplitude amplification was invented for this purpose. So all we need to do is we need to use amplitude amplification to boost the probability of getting the zero state. And for those who are not so familiar, amplitude amplification is like an extension of Grover's algorithm. So Grover's algorithm boosts the probability of getting a marked state, right? And amplitude amplification is just a generalization of that. And so you have to repeat the entire sequence of unitaries, basically 1 over square root of p success times, but p success was 1 over dE kappa. And that's why 1 over square root of p success is square root of dE kappa. And this is the runtime that I gave a couple of slides ago. So now we're going to go into the last part of this presentation, which is an application of our algorithms. So we're going to talk about pretty good measurements. Now, pretty good measurements are really interesting because they enable you to do kind of a quantum state discrimination task. And more concretely, if you are given an ensemble of mixed states, let's call them sigma x, and a quantum state rho, which you don't know, and you're promised that rho is in one of these states with probability px. Now, how can you identify which x is the correct one? Or in other words, which POVM maximizes your probability that you correctly identify rho? It turns out that we actually don't know the answer to this question when you have more than 3 states to discriminate between. But something called a pretty good measurement does pretty well on this task. It turns out that, well, I won't be writing down the form of the pretty good measurement because that's a bit involved. But it turns out that you can, this is a special case of the Petz map with certain choices of the implicit input state and a particular channel which corresponds to a partial trace over the classical system. So since this is a special case of the Petz map and we have an algorithm to implement the Petz map, then we can just use our algorithm to implement pretty good measurements. And if you work out the gate complexity, you need square root of number of states times poly kappa uses of the unitary preparing sigma. So it turns out that what I described on the previous page was, or the algorithm that I described on the previous page was extremely general, in a sense that it assumed that you wanted to discriminate between mixed states. But in general, you can think of the special case of this problem where you just want to discriminate between pure states and they're distributed uniformly. So I'm just going to conclude with why you should care about pretty good measurements. Well, firstly, again, they're very useful in quantum Shannon theory. You can use them to approach the Holyfield information rate. And secondly, they're actually a really important proof technique for algorithms. So, and the reason is because it all boils down to what I said just now about the pretty good measurements being the optimal measurement to distinguish between states. So there's this particular problem in quantum that there exists a quantum algorithm for, and that problem is called the dihedral hidden subgroup problem. And it turns out that using the pretty good measurement, that actually enables you to get the best complexity for this problem. And more recently, the pretty good measurement also appeared in quantum probably approximately correct learning, or quantum packed learning. And there it was also used as a proof tool to bound the sample complexity. So here are some takeaways of this presentation. I guess I even finished ahead of time. So the quantum singular value transformation is really a toolbox that enables us to be systematic, rigorous, and fast, where in the past we were only able to be heuristic. And our algorithm so we presented two algorithms today. Our first algorithm solved the polar decomposition problem. The polar decomposition is a tool from classical linear algebra. So because the way we solved it involved enacting the polar decomposition on a quantum input state, so we considered this to be part of the quantum linear algebra toolbox. And this immediately led to an algorithm for the Procrustes problem, which in turn speeds up implementing pretty good measurements for the special but rather common case of pure states and uniform distribution. The second algorithm we presented was an algorithm for Petz recovery maps and also a general purpose pretty good measurement. It turns out that actually the second algorithm leads to something even more general than pretty good measurements, but pretty good instruments. And the reason this is relevant and interesting is because previously Petz recovery maps and pretty good measurements were just theoretical tools used a lot in proofs. People would say, oh, if we can implement a pretty good measurement, then we can get such and such sample complexity, which is optimal. But now we are actually able to implement these theoretical tools on a quantum computer. And secondly, even though I didn't mention this, our algorithm turns out to be almost optimal in gate complexity. So that's actually the end of my presentation. So what do I do now? Do I answer questions?
Yes, so thank you very much, Yihui, for that very interesting and very well explained talk on some very interesting algorithms. So whilst we wait for questions to come in on Slack, just to add, Nathan added thanks to the question of his you answered midway through, and we're beginning to get some kind of claps and things in on Slack. So I think we can say it's been well received. So whilst we see, I think I can see somebody typing in the Slack, so I assume that's going to be a question. But I had a quick question whilst we're waiting for that one. So when I think it's on about slide 27, you mentioned use amplitude amplification. Do you know P success in advance, or do you have to do amplitude estimation as well in this step? I didn't quite catch that.
Oh, yes, I think in general, that's actually a really good question. I think you would know P success in advance because in a real situation, DE is, so in a real situation, firstly, you would know the channel whose Petz map you want to implement. And you would also know the implicit input state. And so I think the kappa there is actually the kappa, which is 1 over the minimum singular value of the channel applied to the input state. But you know both of these things, so you can compute P success in advance.
Okay, that's fine. Thank you. Yeah, I can still see the Slack saying people are typing. So just another. I wondered, you alluded to this twice, the fact that it's nearly optimal. I wonder, is that just out by logarithmic factors, you mean, or would you be able to say a little bit more about that?
Oh, yeah. Okay, so I'm going to go to the theorem statement. Yes, here it is. Okay, so what we proved is that so we use a Grover's type argument to argue optimality. And the core idea there is that Grover's search is actually just an implementation of the Petz map for a particular choice of input state and a particular choice of channel. And Grover's search actually has a lower bound on the number of times you need to use the kind of the oracle, which in this case corresponds to the forward channel. Of course, I haven't made this entirely clear, but Grover's algorithm has this lower bound. And that lower bound corresponds to square root of the initial success probability. And so it turns out that applying this Grover's search argument gives us a lower bound on the scaling in DE and the scaling in kappa. And it turns out that any algorithm for this problem has to scale as DE to the alpha times kappa to the beta, where alpha plus beta is at least half. And what we have here is alpha is half and beta is half. So we're at most quadratically worse than the best possible thing that you can do.
Okay, thank you. So I notice Nicholas Koukleidis has actually asked the same question, but he's also asked, is this the first efficient algorithm for the implementation of Petz recovery maps?
I think it's the first algorithm for the implementation of Petz recovery maps, period.
Okay, so that's very clear. I can't see anybody else typing, and so being as we've had a few minutes for questions now, I'm going to thank you on behalf of everybody again for this this great talk, and I'm going to end that there. So thank you for everyone who's come to this session and all the other speakers as well.
All right, thank you for having me. Hope you guys had fun and learned something. And oh yeah, I wanted to shout out to Nathan Fitzpatrick. Actually, I'm actually very interested in how these techniques can be applied to condensed matter problems. So it would be really great if you could, if you could have a look and tell me what you find. So thanks very much.